Welcome to this lecture on polynomials. We will continue our discussion from last time and let us recall the main concepts that we need. In this lecture, we will be proving what is called Euclid's theorem for polynomials. And what we need to know is what is the meaning of division. So what is meant by dividing a polynomial with another? We say qx is divisible by px, where px is non-zero if you can write qx as a product of px and some other polynomial. Okay. We discussed this division with remainder theorem. So if we have two polynomials px and dx and dx is non-zero, then there exists unique qx and rx such that px can be written in this fashion, which can be read as divisor into quotient plus remainder, where the remainder has degree strictly smaller than the degree of dx. Okay, so of course we need to know what is meant by degree. We discussed this properly, so let's not go there. I think I forgot about the notion of monic polynomials, so let me define it here. It's a very simple definition. So you pick a non-zero polynomial, call it px, is called a monic polynomial if its leading coefficient is 1. So, for example, this is monic while this is not monic. So the leading coefficient here is 1 while here it is 2. So the first one is monic and this is not. Just a very simple definition. Okay. Here is one problem for practice, and I have defined monicness for convenience again. It's a very simple problem just to practice something that we have learned. All right. So we need the notion of relative primality. Fix a field f, fix two polynomials px and qx. I like fx and gx, but let's say px and qx, not both of which are 0. So the notion of relative primality will apply only when not both are 0. One of these can be the 0 polynomial, but not both of them. So in that case, we say px and qx are relatively prime or coprime, also called coprime, if something happens, if whenever, so whenever dx is a monic polynomial. So monic polynomials are automatically non-zero. Monicness is defined only for non-zero polynomials. A non-zero polynomial is called monic if the leading coefficient is 1. So we say px and qx are relatively prime if whenever dx is a monic polynomial dividing both px and qx, then dx must be this guy. So the only monic which divides both of them is the most obvious one, this guy. Note that every constant polynomial divides everything, which is why we need monicness here to make this statement. If we slash out the monicness here, 2 will also be there. I mean, let's say we are working with the real number field. 2, 3, 2.5, 7, pi, everything is a legitimate polynomial. Even though it is a field element, you can think of it as a polynomial of degree 0, and each of them will divide any polynomial that you throw. So, I mean, one needs this monicness just so that there is a concreteness to it. Anyway, so that's the definition of monicness. That's the definition of relative primality. And here is an example, very simple example. So you pick polynomials. Again, the base field is R. And let's say x plus 1 and x plus 2 are your two polynomials. Then these are relatively prime, while the following are not relatively prime. So you take x squared plus 3x plus 2 and x plus 3. These are not relatively prime. So these two are not relatively prime because x plus 3 divides this and x plus 3, well, hopefully divides that. Let me check. So if you kind of factorize this, what do you get? You get, maybe I made a mistake. So this is x plus 2 times x plus 1, is it? So no, so I should have written x plus 2 here. X plus 2 times x plus 1 is this guy. So these two are not relatively prime. Okay, so these two are relatively prime because just suppose something divides both of them, then it has to have degree at most 1. If dx divides a non-zero polynomial px, then the degree of dx is at most the degree of px. And you will easily see that there is no degree 1 polynomial which divides both of them. One way to see that is the following. If dx divides both of them, then dx also divides their difference. The difference of these two is 1. So if dx divides 1 and dx is monic, dx has to be equal to the polynomial 1. And these are not relatively prime. I'll leave you to figure that out. Again, if dx is a polynomial which divides both of them, it has to have degree at most 1. Then you make your cases and you will be able to prove that these two are not relatively prime. All right, so let's proceed. This is a definition, which will be a key definition. And here is a very simple observation. Not a very simple one, but a very important one. So the observation is, suppose px and qx are relatively prime, and we can write px in this fashion. So suppose there exist ax and rx such that this equation holds, then the relative primality of px and qx implies the relative primality of qx and rx. So the statement is the following, or the observation is the following. If px and qx are relatively prime, then qx and rx are relatively prime. So that's the statement. And why is that? So suppose dx is a factor, is a divisor, is a monic divisor of qx and rx, where we are assuming that these two are relatively prime. So assuming px and qx are relatively prime, we want to prove that these two are relatively prime. So suppose we have some monic divisor, we want to show that this divisor is 1. But if something divides qx and rx, then it divides px also, because if you divide qx, you divide that, and you divide rx, we are assuming that. So dx divides the sum of these two because it divides the individual parts, and therefore it divides px. But then dx divides both qx and px, and since dx is monic, it has to be 1. And that's the proof. I don't think there is any point writing it. You can easily write down the details in your notes. So this is an observation which will be very useful. And now let us proceed. So this is the theorem. Suppose px and qx are relatively prime polynomials. Then there exist two polynomials ax and bx such that this thing, which is difficult to say how to express it verbally, but this thing is equal to 1. So if you are familiar with elementary number theory, which actually is a very good idea to familiarize yourself with at this point, or if you haven't seen it, then maybe you can go there, and all of that is what motivates this. In elementary number theory, we have a notion of relative primality, and we have a similar theorem which was proven by Euclid. Euclid never proved anything about polynomials as far as I know, but it's a theorem of very similar spirit and very similar proof. So it is aptly called Euclid's theorem for polynomials. This one is only for relatively prime polynomials, but we will prove one which applies to all polynomials. So once again, if you have relative prime polynomials, then you can find two other polynomials such that this sum is equal to 1. Okay, so we will use the well-ordering principle. Just like one proves this for integers, the same kind of proof will be given. So here is how it goes. So suppose not. Suppose this is false. Then there are counter examples to this proposition. So you can find polynomials px and qx which are relatively prime, but for which you cannot find ax and bx satisfying this equality. So we will pick a smallest counter example, smallest in some sense. So then we can find a pair of polynomials which serves as a counter example to the theorem, such that the value of this entity, minimum degree, is smallest possible. So what's going on? Basically, this is a notion of size on a counter example, and we are picking one counter example of smallest possible size. This is not to say that there is a unique counter example of the smallest possible size. There could be multiple counter examples, all have the same size and all have the smallest possible size. And by size, again, I mean this. Also note that if this is to be a counter example, you cannot have either one to be 0. If qx were 0, you can easily show that, if one of these two were 0, you can easily show that this cannot be a counter example. Because if this is 0 and you have relative primality, then the only way that can happen is the other guy is a constant polynomial, meaning a polynomial of degree 0. Of course, both of them are not 0 simply because they are relatively prime. When we defined relative primality, it was only for two polynomials, not both of which are 0. So all I'm saying is that if you have a counter example, then both of them are non-zero. Because as soon as one becomes 0, you can prove the theorem for that particular pair. Alright, so just let us note that px and qx are non-zero. Okay, so we pick up counter example of minimal possible size in this sense, and we may, without loss of generality, assume that degree of px with at most degree of qx. Right? One of them will have greater or at least as much degree, so just call the smaller one px. Alright, and now we will use division with the remainder theorem. So division with the remainder theorem gives that we can write qx as px times some capital Qx plus Rx. Okay, and this is division with the remainder. Where what happens, where degree of Rx is strictly smaller than degree of Px. Alright. And now, here is again a very important observation, if you will. Then Px and Rx are relatively prime. And this is what we observed in the previous slide. If Qx and Px are relatively prime, then Px and Rx are relatively prime. Okay, but the size of Px Rx pair is strictly smaller than the size of the Qx Px pair. Or Px Qx pair, it's the same thing. So this is strictly smaller than that, very easy to see. And therefore, the pair Px Rx cannot be a counterexample to the proposition. Because, well, these px and rx are relatively prime, but they have strictly smaller value of the notion of size that we imposed. So this doesn't serve as a counterexample, and hence one can find, meaning theorem is true for this particular pair, and thus we can find two polynomials such that px times ax plus rx times bx is 1. But now just substitute the value of rx. I'm kind of running out of space, so let me make some space. So here all you need to do is just write down the expression of rx in terms of qx, px, and that guy. So rx is nothing but the difference of qx and that is what we will write here. So we get, therefore, this is equal to 1. And now if you just rearrange things, you will find that this implies px times this thing plus this is equal to 1. And just call this little ax, call that little bx, and you see that this equation is true. And this contradicts our assumption that, this contradicts the choice of the counterexample. Px and qx were a counterexample, so we couldn't have found such things, but we have found such things. This is a contradiction, and therefore there cannot be any counterexamples. Right? So that's it. So this proves Euclid's theorem. This proof is exactly the same as the proof for integers, except that here the notion of size is in terms of degrees. So yeah, fine. So this is Euclid's theorem for relatively prime polynomials, but we want to prove it for general polynomials, and for that we will need the notion of the greatest common divisor. So fix a field f and fix two polynomials px and qx. Again, not both of them are 0. Then a monic polynomial dx is called a greatest common divisor, or GCD for short, f px and qx if two things. It must divide both of them. So here is a notation for division. It's just very, very convenient. Dx divides px and dx divides qx. So you can just read this as divides. Dx divides px, dx divides qx. So this is necessary condition that we need, and the other condition that we want is that whenever you have another common divisor, so if you have a non-zero polynomial which is a common divisor of px and qx, then it must divide dx. So if ex divides dx, in some sense dx is bigger than ex, and what we are saying is that you call dx the GCD if, first of all, it is a common divisor. So it is a common divisor, and it is greatest in this sense. Okay. So here is, the definition should be clear, but here is a very simple observation and an important one that you can prove it as an exercise. So two polynomials are relatively prime if their GCD is 1, or if 1 is their GCD. So one thing we should be, we should have said is that the greatest common divisor, a priori, the definition cannot demand uniqueness out of it. The definition just demands the satisfaction of these two properties. But it turns out that there is only one polynomial dx that satisfies these two properties. So we will show that the greatest common divisor exists and is unique, and perhaps only then this lemma will make sense. So let me not write it here. Fine. So now we want to show that the greatest common divisor exists and is unique. So here is, let me not write the statement. The statement is the existence and uniqueness of GCD. So fix two polynomials, px and qx. I like fx and gx. Let me write fx and gx. Let fx and gx be two polynomials over a field f, and not both of them are 0. First, let us prove the existence of GCD. So define this set, fancy D, as those things in fx, those polynomials which are monic, hence non-zero automatically, and which are divisors of both fx and gx. So just collect all the monic common divisors of fx and gx. This is a non-empty set because the constant polynomial 1 is already here. The polynomial 1 is here, so this is a non-empty set. Okay, and since this is a non-empty set, and the degree of anything here is at most the degree of the non-zero one amongst fx and gx. So let's say fx is non-zero just for concreteness. So here let me just write that down. Fx is non-zero. Without loss of generality, we can assume that fx is non-zero because not both are assumed to be 0. So since dx in particular divides fx, the degree of dx cannot be larger than the degree of fx. And therefore, all the things here have bounded degree. Degree, in fact, is bounded by the degree of fx. So we can pick one with the maximum possible degree. So dx be of maximum possible degree. So we are not saying that there is, a priori we cannot say that there is only one such guy. Amongst all the members of D which possess the maximum possible degree, you pick one, call that dx. So we will show that dx is a GCD of fx and gx. That is what we claim. Okay. So first of all, dx is a common divisor. So we can write dx as, or rather we can write fx as dx px for some px and gx as dx qx for some qx, because this is a common divisor of fx and gx. And now just note that we are proving the claim, the thing here, we are proving this. So now note that px and qx are relatively prime. Why is that? This is where we'll use this. So if px and qx were not relatively prime, we could have found a common divisor of px and qx of degree strictly greater than 0, meaning strictly or degree at least 1, in other words. So if you have some let's say capital dx of degree at least 1 dividing both px and qx, then dx times capital dx will divide both fx and gx, because just write px as capital dx times something and write qx as capital dx times something. So dx times capital dx and dx times capital dx, it divides both fx and gx, and the degree of this is strictly greater than the degree of little dx, because this guy has degree at least 1, and that contradicts the maximality of this degree. So we can always choose capital dx as a monic polynomial here in the entire thing that I said. You choose that as a monic polynomial, you will get that this is also monic, because product of two monic polynomials is monic. And then we would have a monic polynomial of degree strictly greater than the degree of dx dividing both fx and gx, and that is a contradiction to the choice of dx. So let's be very clear about that reasoning. So that is the reason why Px and Qx are relatively prime. Okay, and now by Euclid's theorem for relatively prime polynomials, we can find capital AX and capital BX such that this happens. I'm not writing the full statement, but I'm sure you follow. So we can find capital AX and capital BX such that this happens. I could have just said small ax and small bx. There is no confusion. And now multiply both sides by dx. So let me multiply it here. Multiplying both sides by dx, we get that, but dx px is fx and dx qx is gx. So this gives okay. All right. And now to finish the proof of the fact that dx is the greatest common divisor of fx and gx, all we need to observe is that if ex is a common divisor, let's say a monic common divisor of both fx and gx, then it divides the left-hand side because it divides fx and gx, and hence it divides dx. So as soon as you have a non-zero common divisor of both fx and dx, I mean, divisors are already non-zero, so as soon as you have a common divisor of fx and gx, then it divides this and hence that, and therefore dx is a GCD of fx and gx. So that proves existence. And in fact, you kind of get an algorithm to find the GCD. Algorithm in some sense, perhaps a useless one, but it is an algorithm nonetheless. Fine. Maybe not an algorithm, but a procedure. Okay. And now to prove uniqueness, just note the following. And this is where we will use the problem that we gave. Like in the beginning of the lecture, we had a problem which was also marked with star, not because it was hard, but because we were going to use it. So if dx and d prime x are both GCDs of fx and gx, then they divide each other. By definition of GCD, every common divisor divides any GCD. So you just switch the roles of the two, you will find that dx divides d prime x and d prime x divides dx. But if two monic polynomials divide each other, they must be equal. This is the problem that we gave in the beginning. So therefore, the uniqueness of GCD follows. And now we can make that statement that we made earlier, which was that two polynomials are relatively prime if and only if their GCD is 1. Okay. So far, so good. And now we can finish the lecture. Euclid's theorem in general. Suppose px and qx are two polynomials, not both 0. And let's say dx is their GCD. This is the notation for GCD. This is now well defined because we have proven that dx is unique. So any two non-zero, any two polynomials, not both of which are 0, have a GCD and they have a unique GCD. So we just have a notation for it, and let's call it dx. Then what we are saying is that there exist polynomials ax and bx such that this thing is the greatest common divisor. So this generalizes the Euclid's theorem for relatively prime polynomials, because if px and qx were relatively prime, dx would just be 1. Okay, so why is this true? I'll just write one line. Say px is dx times capital Px and qx is dx times capital Qx. And note that since dx is the greatest common divisor of px and qx, the greatest common divisor of capital Px and capital Qax must be 1. So this just justify for yourself and apply Euclid's theorem for px and qx. So if you apply Euclid's theorem for relatively prime polynomials, which we have proven, so you apply that for capital Px and capital Qx, you will be proving this. So I'll leave the details for you to fill. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.